Hello guys, welcome to Physics for Smart Brains. Today we will discuss about the diodes. I will show you one, how it works, and then I will show you how to build your own bridge rectifier. So a diode basically consists of silicon wafers which are infringed with different impurities. There are two types, N type and the other one, P type. The N type and P type depends on the type of impurity added. The purest form is of silicon. If we have a look at the wafer of silicon, it is something like that. Silicon have 4 electrons in the outermost shell. So the one of this silicon is bonded to the other of that silicon. So they form full octet bonds like this and continue in the same manner. But in case of N type, an impurity from the 15th group is added. They have 5 electrons in their outermost shell. So let's assume if we add that phosphorus, it will have 5 electrons. 1, 2, 3, 4. 4 will form the bonds with the other silicons, but the one will remain there. That one will be create an excess of electron over there and help in increasing the conduction. So this is how the N type works. For a P type, we'll have a look at the same type of silicon structure, but here we will take gallium, which is from the 13th group as impurity. It will form bonds, but it has only 3 electrons in the outermost shell. So what it does is that it creates or leaves an empty space, and there is 1 electron. 1. It creates a hole or a vacancy for an electron. Now what happens is that electrons from the surroundings come to occupy that hole, and when electron reaches this, they create another hole there. In this fashion, conduction increases greatly. Okay, now we will see the working of a diode.
Diode. A diode is a semiconductor device which is used for many practical applications. Today's modern technology is based mainly due to diode. Now let's see the working of a diode. First of all, I would like to show you how a diode looks like. This is a diode where this is the N terminal and this is the P terminal. Now let's see basically what it is. We take a silicon wafer and using a photographic plate we cover the half side of this and like that, and on the other half side we dope it with the pentavalent impurities, so it will be an N type. Since we have pentavalent impurities, there will be an excess of electron, that's why N type, but the charge on this will be 0. And now we cover it the other half with the photographic plate and we add the trivalent impurities to this side and it will form the P type, and thus our diode is formed. This is how a diode looks like. This is a complete silicon wafer. We get misconceptions like we join 2 wafers, one is P and another is N, to make a diode, which is just a misconception. We don't do actually such since we can't get so much good interactions due to joining 2 wafers. So it is always a single piece of silicon or germanium wafer. So now let's see the basic mechanism behind this. On the P side we are having the holes in excess where the electrons in very less quantity, whereas on the N side we are having electrons in very large numbers as due to the pentavalent impurities, and the holes as minority carriers. So here the electrons are the majority carriers in the N type part, and in the P type part we have the holes as the majority carrier. when no electric field is applied, that is no potential drop no potential is applied across the diode, then the electrons, due to a concentration gradient, here the concentration of hole is higher, so they would tend to move to the lower concentration, that is they will go like that, and the electrons would tend to go to the p part like in that way, and hence we will get to see a depletion region. A junction will be formed at the center like that. In the diagram we are getting to see, since the holes are since from here the electrons are going to the other side, so this part will become positively charged and this part will become negatively charged like that. This is p type, this is n type, and so we see that a junction is formed, and the electric field will be set up between this junction. Can you guess in which direction will electric field will set up? It is from plus to minus, so it will be set up in this way. Now this electric field will create a potential difference between these two junctions, and that is known as the barrier potential or the potential barrier. This stops the further movement of the particles from both sides. Holes we can't say as a particle, since these are just imaginary vacancies and which have less mobility than the electrons. Now what to do with this? For doing that, we apply a potential difference across it, and this potential this process of applying the potential difference across the diode is known as biasing. We have two kinds of biasing. First is the forward biasing and the other is the reverse biasing. In the forward biasing, we connect the P part to the positive terminal of the battery, whereas in the reverse biasing, we connect the P part to the negative terminal of the battery and the negative terminal of the battery to the P type and the positive terminal of the battery to the N type in reverse biasing. There are many applications we find in forward biasing as well as in reverse biasing. Let us see first the forward biasing. Also, the symbol of the diode is like that. This is often the symbol where this is the positive terminal, that is P type, and this is negative terminal, that is N type. But we see it in the actual diagram if it is in the forward biased. When the diode is in the forward bias, see that the positive is connected to the P type of the diode, then the holes here feel a force of repulsion. Since this is a positive and these particles are assumed to be positive charged particles, then they will get a force of repulsion over here, and at the negative terminal we have electrons which will get also a force of repulsion, and they will there will be no more the junction over here and current will flow along the diode. But in the reverse bias, we have like that. This is P and here the negative is connected to P, so the holes here, electrons here, holes are there. Now the holes will get a force of attraction over here and this also over here, and so the depletion region will become more thicker and thicker and the current will not flow. We see that here the current is of the order of microamperes, and whereas it is in the order of milliamperes in the forward bias. So for a good amount of current we use in forward bias, and for some other purpose we have to use in reverse bias. The forward characteristics we get for a diode is like that, where after a certain voltage this is IV characteristics, the V versus I curve of the diode of the semiconductor devices is known as the characteristics curve. Here this is known as the cut-in voltage, after which the voltage and current rapidly increases, and for the reverse bias it's like that. This is known as cutoff voltage, or also known as the breakdown voltage, since after that current increases very rapidly with a very small change in voltage. See that this is very small change in voltage and the change in current is very rapid. We will also find an application of this in here we have seen that the potential barrier and this applied potential both are opposing each other. So we have broken off this potential, and so after some time it will have very less, the junction will become very thin, and so the majority carriers can easily flow and the current will rise, whereas the applied potential is in the same direction of the barrier potential. Hence it becomes thicker and thicker, and the flow of majority carriers is not possible. So this is for our physics for smart brains, the working of the diode. Hence in the forward bias it conducts and it opens as if it is an ideal diode, it behaves as it is short circuited, whereas in the reverse biased, for an ideal diode it behaves as an open circuit. But for a practical diode, where there is very small resistance of this diode and it is just behaves like an short circuit.
The diode can be used to create DC output from AC. Let's see how we can do that from the following circuit diagram. Let's assume that here it is positive and here it's negative. When it's positive, this diode will work, conduct, and this will not, because it is in forward and it's reverse. So hence current will flow. Also in this direction, this diode is reverse, it will not work and it will work. Current will flow like from here, and then we'll receive the output. We will receive here positive, here negative. The next time we will do this, let's assume here it is negative, no positive. This time this diode will work, this doesn't, and this works. This will receive the positive, and it will get positive this time also, and negative this time also. So we can see that it is same direction, we are getting same direction electricity, and it's DC, but it is not constant. So what we do is we fit a capacitor here to smoothen the voltage. The normal input was something like this, and output that we received is this. These are the voltage peaks, and after the application and joining of the capacitor, it will using the capacitor, the waveform is now quite similar to that of DC. Thanks for watching us on Physics for Smart Brains. If you like our video, then please subscribe our channel too.